Hello everyone, my name is Pranil, and today we're diving into the world of multivariable calculus to understand increments and differentials. These concepts will help us analyze how small changes in variables, like x and y, affect a dependent variable z. So why is this important? Well, understanding this is crucial for real-world applications. For example, when designing a machine, modeling physical systems, or even training a machine learning model, we care about how small changes in one factor influence the system as a whole. We'll start by understanding increments and then define total differentials. Finally, we'll tackle two examples to help apply these concepts step by step. So, our first concept: what are increments? So the formula for increments is that delta z is equal to f of the quantity x plus delta x, comma, y plus delta y, minus f of x, comma, y. Increments describe the total change in z when both x and y are changed by small amounts, delta x and delta y. So why do we subtract f of x plus f of x, comma, y? Well, that's the starting value of z. Without subtracting it, we wouldn't actually know how much z changed. This is really similar to the equation y is equal to mx plus b, where b is your y-intercept. We don't necessarily care about b, we just care about m, which is why we're subtracting the y-intercept, so we just get the absolute difference. Now, what happens when delta x and delta y are really small? Well, mathematically, they approach zero. This leads us to our next concept, the idea of a differential, which measures infinitesimally small changes. So, what are differentials? What are differentials? Well, let's define dx and dy as infinitesimally small changes in x and y. They represent tiny steps in these variables. The corresponding change in z is called dz, and it would be given by this formula. dz is equal to partial z over partial x dx plus partial z over partial y dy. Now this formula might look complicated, but it's pretty simple. The formula has got two terms. The first term is partial z over partial x dx. Now this term tells us the change in z due to x while keeping y constant. This tells us the change in z due to x keeping y constant. Alright, and similarly, partial z over partial y dy, well, this measures the contribution of y keeping x constant. So it measures the contribution of y keeping x constant. So why are we using partial derivatives here? Well, that's because z depends on two variables. Partial derivatives isolate the effect of each variable. So what happens if either dx or dy is 0? Well, then the contribution from that variable disappears. Then we'd simply drop them in the formula because their value would equal 0. This is a key insight. Now, let's abstract this topic a little bit and go into the total differential for multiple variables. Let's go into the total differential for multiple variables. Now, If z depends on more than two variables, say our variables are x, y, and u, then the formula simply expands to include all the variables. So we would have dz is equal to partial z over partial x dx plus partial z over partial y dy plus partial z over partial u du. And this would obviously go on for how many ever terms you have. If you have 5, 6, 7 variables, no problem at all. Just make sure you isolate the effect of every single variable and add it to the formula. So each term in this formula represents how z changes with respect to one variable, assuming all the others are fixed. If one variable does not influence z, like u, then partial z over partial z equals 0. And that corresponding term simply drops out. Alright, now this is great, but let's go into an example. Example 1. Let's say that z is equal to 2x sine y minus 3x squared y cubed. What is the total differential of this equation? Well, this is pretty simple. First, let's write our formula. dz is equal to partial z over partial x dx plus partial z over partial y dy. And it ends there because there's only two variables in our equation, x and y. And so let's calculate partial z by partial x. To calculate partial z by partial x, we treat y as a constant. So let's differentiate each term with respect to x. The first term is obviously 2x sine y. The derivative of 2x is 2. So partial z over partial x. The derivative of 2x is obviously 2. So this becomes 2 sine y, since y is a constant. And then our second term becomes our second term is negative 3x squared y cubed. And the derivative of negative 3x squared is negative 6x. So it becomes negative 6xy cubed. Sorry, negative 6xy cubed. So putting it together, partial z by partial x is just 2 sine y minus 6xy cubed. Now let's calculate partial z by partial y. Now we're creating x as a constant. So our first term, 2x sine y. Well, the derivative of sine y is just cosine y. And since 2x is a constant, it becomes 2x cosine y. And the second term, negative 3x squared y cubed. Well, the derivative of y cubed is 3y squared. So this becomes negative 9x squared y squared. So putting it together, partial z by partial y is 2x cosine y minus 9x squared y squared. Now, let's put them back into our original formula, this formula over here. So, in total, dz is equal to the quantity 2 sine y minus 6xy cubed dx plus 2x cosine y minus 9x squared y squared, I'm running out of space, dy. So this is the total differential. Each term shows how x and y individually contribute to changes in z. Alright, let's look at the second example. Example 2. Let's say that z now is equal to x squared y plus y squared plus t squared. Let's write the formula for dz. In this case, dz would equal partial z over partial x dx plus partial z over partial y dy plus partial z over partial t dt. Now let's compute all the partial derivatives. Partial z by partial x is just going to equal 2x. Since both y and t are constant, they just get cancelled out. Similarly, partial z by partial y is going to equal 2y. And partial z by partial t is going to equal 2t. So what does this mean? This means that dz is going to equal 2x dx plus 2y dy plus 2t dt. This formula tells us the total change in z based on changes in x, y, and t. If t is equal to 0, the dt term disappears, simplifying the differential. So let's do a recap. We learned how increments become differentials and derive the total differential formula. Then we applied it step by step to two different examples. Now I want you to think about this. If dx, dy, and dt are all 0, dz also becomes 0. This tells us we're at a stationary point, where z is not changing. Now, where else might this concept be useful? Think about gradient descent in machine learning, fluid dynamics, or even optimizing business processes. This is useful everywhere. Thank you guys for following along. Make sure to keep exploring math because it's the key to understanding so much of the world around us.